Good morning to everybody. We can start the lesson of today. Okay, so let's close our discussion about ceramic composite materials. We were discussing last time about reinforcement. Let's close the item talking a little bit about the materials which can be used for the matrix of the composites. Usually, we have to say that the selection of the matrix material is controlled by thermal stability, because we are thinking about materials that have to work at high temperature, and also processing, that is fabrication consideration. The melting point is a good fourth indicator for high temperature stability, but however, we need to remember that higher is the melting point, more difficult is the fabrication process. There is also another issue that's very important, which is going to be focused on mechanical and chemical compatibility of the matrix with the selected reinforcement. This means that we can have chemical effect, that is reactions, that depends on the materials that which are coupled, but we can also have mechanical effects which must be controlled, because they can affect the level of the residual stresses or of the stresses inside the composite itself. And for this, just let us remember that if we, for example, take a simple case, fiber matrix, having two different values of the thermal expansion coefficient, that is, there is a mismatch between the thermal expansion coefficients, obviously, since we are thinking about a component which has to work at high temperature, the effect of different strains related to different values of the thermal expansion coefficient can be relevant. And in the case in which the thermal expansion coefficient of the matrix is higher than that of the fiber, obviously in this case by heating, we will have radial compressive stresses in the matrix and tangential tensile stresses in the matrix, that is also the interface, and this is important for interface integrity. Instead, if we have the opposite condition, that is the thermal expansion coefficient of the matrix is lower than that of the fiber, we will have radial tensile stresses and compressive stresses as a tangent stress. So the selection must take into account these effects, mechanical effects, which can be calculated very simply, because we do have a very simple geometrical configuration. That's a cylinder which represents the fiber with the matrix which is located around the fiber itself. So calculation is not very complicated. And when we can, the general line is to always select materials, depending obviously on the application, for which the difference between these two values of the coefficient of thermal expansion is reduced as much as possible. Here you have a table in which I have reported the, let me say, most used materials for fabrication of the matrix of the composites, and you see they are not so much, in which you have main of the mechanical resistance properties. What we can see is that the fracture toughness, as we can expect, it has low values. And this gives rise to values of resistance in tensile, here reported as modulus of rupture with the UK unit of measurements, KSI. You must know the equivalence. That's not very complicated, but values which are very low, as we have said last time, with respect, for example, to the same values, but refer to the fibers having the same composition. The fracture toughness is not going to change, but the maximum allowable tensile stress is going to be increased in a relevant way if we move from the bulk monolithic that represents essentially properties of the matrix to the fiber solution. Just to have some figures for you. One very interesting case of matrix materials, they are mentioned here in the table where you find LAS, glass ceramic. Now we will say something about that, is the possibility to use classes which belongs to ceramic materials, but they are named for their peculiarity, glass ceramic materials. You can easily recognize when we speak about the glass ceramic materials because they have very strange, let me say, denotation, like in the last sentence here, LAS, MAS, and so on. This corresponds to a consolidated notation where L stands for lithium oxide, A stands for aluminum oxide, S stands for silicon oxide, M for magnesium oxide, etc. C, calcium oxide, and B, barium oxide. So if you read LAS, this means that we have a glass ceramics which is made by, as composition, lithium oxide, aluminum oxide, and silicon oxide, and so for the other. Why these are interesting? Why these are interesting, even though they do have some limitation? Because they are glass, but, and that's the meaning, glass ceramics, so they do have some of the behavior which are typical of glass materials. Remember that when we talk about glass, we have in mind amorphous materials, but they are polycrystalline. So they do still have some of the behavior of amorphous, but if we look to the microstructure, they are polycrystalline. And it is possible with this composition to have a controlled crystallization of the glass itself, resulting in randomly oriented crystals with some very low percent values of residual glass, that means amorphous phase, which is in between 2 and 5%, with, and that's important, no voids or porosity. They are essentially, as we see here, belonging to the class, if we want to maintain our distinction, of the oxide ceramics, but they are special inside the class of oxide ceramics because they retain behavior of the glass, of the amorphous glass. The standard one, let me say, that we have in mind are the silicon oxide based glasses. And they are interesting because they are quite easy to process, since we can rely on the viscous behavior, which is typical of the glasses, and so we can use a viscous sintering technology, which is much easier and much faster than the standard solid state sintering without the presence of a liquid phase. And so they introduce, let me say, some facilities in terms of easy of fabrication or of easy of processing. However, they cannot be used due to the properties of the basic compounds for temperature which are higher, if we go to the extreme, higher than 1200 Celsius. They have, that's another interesting thing, higher strength and toughness with respect to classical glasses. And this because we do have compounds in addition with respect to silicon oxide. And also, as it happens with glasses, the properties, for example, the thermal expansion coefficient of glass ceramics can be controlled by adjusting the composition. And inside, we already mentioned sometime, I don't remember when, during our discussion, but we can have formulation, for example, of lithium aluminum silicate, LAS, having a thermal expansion coefficient which is nearly zero. That means that they have a very good thermal stability, not in terms of reaction with the environment at higher temperature, but in terms of dimensional stability, because they do not have values of the alpha coefficient, which is, let me say, sensibly different from zero. And here you have some example of glass ceramic matrices in which I have not reported the formulation, because that's a general overview, for which the value of the thermal expansion coefficient is nearly equal to zero. But as you can see here, with respect to the classical glass materials, we do have something which is around one multiplied by 10 to minus 6 as values of the thermal expansion coefficient. And then, with respect, as we said before, to the classical glasses, if you look to the fracture strength, that is the tensile resistance of the materials, you see that we have as an average values which are higher than those of the classical glass materials, maintaining, in any case, since that's a general feature of the ceramic materials, values of mass density which are around 3 grams per cubic centimeter. So they are interesting for these reasons, and some special application of glass ceramics as matrix materials for ceramic composites can be found in very, very specialized situations. If we move to, for a moment now, with our classical distinction between oxide and non-oxide ceramic materials, having said, and then we already put our attention on the special class of glass ceramics, we can say that for non-oxide materials used as metrics for our composites, essentially looking to the few applications very performing that we can meet, we do have carbon, we do have silicon carbide, and we do have silicon nitride. And among these, let me say, the materials which have been experienced a higher number, even though they are low, of application are matrix made by carbon, then it follows silicon carbide, and then last it follows silicon nitride. Carbon is a very refractory materials, having, let me say, a decomposition or a melting temperature in boil without oxygen. Otherwise, we have reactions which is higher than 3,500 Celsius, and has a low density with respect to the average density of ceramic, because it stands around 2 grams per cubic centimeter instead of 3. But as a drawback, that is for high temperature application where we do have oxygen, it can go under catastrophic oxidation thanks to the reaction of carbon with oxygen, with the formation of, for example, of carbon dioxide, just an example, or carbon monoxide, that depends on the partial pressure of the oxygen present. And so it must be protected if we want to avoid this deterioration mechanism. And this is really a deterioration mechanism, because if we are going to form by a solid materials, carbon, a gas, carbon oxide or carbon monoxide, obviously we are losing our solid part. Silicon carbide, instead, it has also a good refractory, let me say, behavior, lower than carbon, because in void, in absence, again, also in this case of oxygen, the melting temperature is higher than 2,500 Celsius, so it's in any case a very relevant figure. So, it has a slight high density with respect to carbon, because it stands exactly around 3 grams per cubic centimeter. And also these materials can experience oxidation in presence of oxygen, obviously, with the formation of silicon oxide or silicon monoxide, taking into account that silicon monoxide is again a gas phase. But these phenomena, which depends on the partial pressure of oxygen, becomes to be very, very relevant so that in this case we need a protection also for silicon carbide only when we are exceeding working temperature in air, that is in presence of oxygen, which are higher than 1,500 Celsius. So up to this temperature value, the behavior of silicon carbide, also in oxidizing environment, not for very long application, can be considered as satisfactory. The last one is the silicon nitride, which has properties similar to silicon carbide, but this is thermally more thermally unstable. And also has lower thermal conductivity with respect to the previous two, and it has been used in very few cases. For example, in Formula One some years ago, with respect to the, again, I want to underline, the number of cases is limited, but with respect to carbon or silicon carbide, silicon nitride is less diffused. In the case instead of oxides, ceramics, matrix, apart from the glass ceramics, which can be met in some special applications, are aluminum oxide, or the mullite, which is aluminum and silicon oxide. Cordierite is called in this way, in which, with respect to the presence of aluminum oxide and silicon oxide, it's a formulation which has inside also magnesium oxide and zirconia. And the class of oxides, matrices, are for sure less costing than the non-oxide materials. They can exhibit a very good sintering behavior, also at temperature which are lower than those requested for the other classes of oxides. And they do have, obviously, a very good resistance in temperature to oxidation, because they do have oxygen inside the formula, so they do not react, apart the case in which they are under stoichiometric, but we usually try to avoid this case. Which are the main limitations about that? Poor thermal expansion, matches with many fibers, especially if we are thinking to the possibility to combine these kinds of oxide matrix with non-oxide reinforcement. So the difference is quite relevant. And then with respect to the other one, that is the non-oxide materials as matrix, they have lower value of strength and low high temperature mechanical properties. Among these four, alumina is the most prevalent, which can be found. For temperature which exceeds 1,000 Celsius, apart from the special case of glass, but ceramics, for which we have put limitation on 1,200 Celsius. So if we want to generalize, let me say, for temperature which are higher than 1,200 Celsius, oxide ceramics are not suitable to be used for the matrix. And so we are going to use non-oxide ceramics with only one exception. And this is the reason, because I told to you before that among that five, alumina is the most diffused, because alumina still can show a temperature higher than 1200 satisfactory behavior. So if we want to, if we have in mind, let me say, very, very high temperature application, usually, and this is the reason we are going to talk about non-oxide ceramic material as matrix. And this then also as a consequence for the selection, due to the fact that I told to you before, that is the chemical stability, that is the mechanical mismatch, let me call it short in this way, with the selection of fibers. So we have non-oxide matrix and non-oxide fibers for very high temperature application of ceramic materials. What about the possibility to fabricate these components? Well, we do have some techniques, obviously sintering, we have already discussed it, which are based, as we said, on sintering. For example, by using powder processing. This is usually made. I'm now talking about practical situation, what is done in the industry, when we do have a discontinuous reinforcement. Okay, sometimes we can find slurry infiltration, that is fabrication by using something which is similar to a liquid, but not for liquid sintering. In the case we have in mind, for example, glass ceramic as matrix, for the reasons that I told to you before. Otherwise, the most common, let me say, known fabrication routes are polymer infiltration and then pyrolysis. That's the same mechanism we have already discussed when we talk about ablative material. And thus we use a resin. We will see an example. We use a resin which is then transformed through pyrolysis to carbon. So we are talking about non-oxide matrix ceramic composites, and chemical bubble infiltration, which is called also CVI, that stands for chemical bubble infiltration. This is an example of a composite materials made by chemical bubble infiltration. What is chemical bubble infiltration? It's a quite simple thing to understand if we remember what is a chemical bubble deposition process. When we talked some time ago about coatings, some years ago, I should say, we made a distinction about surface engineering technologies, looking to those technologies which are usually used for the fabrication of the so-called thick coatings, as an example, thermal barrier coatings, which are essentially based on thermal spraying technology, that is plasma spraying or HVOF, and then the class of the so-called thin coatings. Thick and thin. Why? Because the thermal spray technology are suitable for the fabrication of coatings having, as an average, thicknesses higher than 100, 150 microns. If we instead need a thin coating, which can be of the thickness of some microns, or also under 1 micron, we need to refer to vapor deposition technologies. And we said that time that we have two broad classes: the physical vapor deposition technologies and the chemical vapor deposition technologies. Physical vapor deposition technologies means that we make an evaporation of the solid phase for which and with which we will realize our coating. And then we do have a condensation of the solid evaporated on the surface, which must be coated. That's very simply PVD. When we talk about CVD instead, we are thinking to the possibility to have at least, generally speaking, two different gases which can react between them. The reaction is made on a surface, that is the substrate we want to coat. One of the product of the reaction is a solid, and this solid is the solid with which we are going to fabricate the coatings. So chemical bubble infiltration is just a CVD process where we do have, for example, a textile of fibers. We force our gases to pass through this textile, and having a CVD process inside, the gases react between them, they form a solid phase, and so they fabricate, let's use this way, the matrix of the composites. And this is quite used for non-oxide matrix and non-oxide fibers. I would say they are the most important processing technology, which are, for example, used for the fabrication of silicon carbide composites. If we look to carbon-carbon composites, like we will see later, the other technology, that is the polymer infiltration and pyrolysis, is instead the most diffuse fabrication technology. So carbon-carbon, we mentioned carbon-carbon. I want to make to you one example, just to remember that they have been used, and again, in very performing application, due to high cost, due to high level of control of processing technology, etc. And at the beginning, they were developed in the 60s, and they were limited in terms of application to military application, such as, for example, rocket nozzle or re-entry part for missiles. Then we add also another kind of application that I will show to you, that is the space shuttle. But from this example, you can again remember that we are talking about very special materials, okay? Depending on the carbonization or graphitization temperature with which we fabricate the matrix, which is usually derived from a pitch, a resin, or a gas containing carbon, the resulting matrix can be amorphous or can move through a graphitic structure. And higher is the degree of graphitization, that is, higher is the level of graphite inside the matrix, the higher is the oxidation resistance of the materials, and higher is the thermal conductivity. But we pay this improvement in performance for what it concerns oxidation resistance and thermal conductivity with the fact that the material itself is more brittle, so less resistance. Again, we are talking about the presence of tensile stresses, and always with this. So depending on the type of application we need, we can select, let me say, a matrix due to the fabrication processes which are used, which can be prevalently graphite or amorphous, but we have to keep in mind that in this case we are moving the final property of the composites without changing the composition, because always it stands for carbon, with respect to the oxidation behavior and with respect to the mechanical behavior of the materials itself. Here you have one example, again, just to lead to you some an idea. of the carbon fibers, which can be used for the carbon-carbon composites. And so you can see, as we have a lot, let me say, of possibilities. That depends obviously on the also for the fibers on the quantity of amorphous or graphite which is present. But if you have a look, for example, to the tensile strength, to this column here, you see we have values for some situation which are very, very high. So depending on the design requirements, we can design our composites, and that is, we can select the basic components. For the matrix, for what it concerns the matrix, which I called also carbon precursors, for the reasons that it will be clear in a moment, the most important criteria for the selection of the matrix are here listed. So the carbon yield, minimal shrinkage during pyrolysis. So this anticipated that pyrolysis is the most diffuse fabrication technology for this kind of materials. High degree eventually of pre-polymerization, because we are going to use a polymer in order to generate our carbon-based matrix. And then obviously cost, which is always for applications a factor that nowadays cannot be more neglected. And essentially three types of matrix systems are used in the industrial manufacturing processes for carbon-carbon composites. Thermosetting resins, like for example phenolics or polyamides. Thermoplastic precursors, this is the meaning of pitch, that is the precursors with which we can fabricate a thermoplastic polymer. And then also the possibility to have deposition of carbon by a gas phase. But the fabrication, as you see here, is even though we have examples of a chemical bubble infiltration, which stands for fabrication technology in which we use a gas phase rich in carbon. The liquid polymer infiltration is the most diffused fabrication technology. Obviously, there is another factor which is very important, having in mind these two. Now, let's talk in general, fabrication routes. The first one, we are going to infiltrate the polymer in our textile of carbon fiber. Then, by pyrolysis, the polymer must be transformed in carbon. In the second case, CVY, we have our textile, and then we are generating carbon through a CVD-like process. So this means that the processing parameters and the fabrication technology must, first of all, is very long, depending on in time, depending on the size of the components that we want fabricate. Then must be properly monitored, because we are going to let me say, in the second case, fabricate a solid starting by a gas, and in the first case, modifying a solid in carbon, which will represent the matrix. And thus we do have a problem of densification, generally speaking, which must be monitored. And densification is a very important issue for these composites, because and also this can be quite clear to us, since higher is the densification, higher is the mass density, lower is the residual porosity, essentially. The mechanical properties are very strongly affected by the densification degree. And obviously, we expect that the densification degree, an increase in the densification degrees, is able to increase the mechanical properties of the materials. Just a couple of examples here, even though that they are not optimal, because you see the first case referring to the same materials used, In the first case, we have something which is around 7% of porosity, which is too much. But if you compare the first two line of this table, you see how we can have a very relevant increase, or let me say, difference in the strength of the materials, but evaluated by the modulus of rupture, we can double more or less. Evaluated by a pure tensile test, last column, we do have 40 to 50% more, which is not neglectable, talking about this class of materials. Carbon-carbon, they do have an excellent high temperature performance. Usually, technically speaking, the figures that I gave to you about refractory properties of carbon cannot be directly translated into the carbon-carbon system because that one, more than 3,000, was in void. But now we are on practical applications, and so we can say that this kind of composites, looking to the figures, to the strength that they can retain without oxygen, that is, when oxygen is not present in the working environment, they do have up to around 2,200 Celsius, very, very good properties in terms of strength, modulus, and creep resistance. But when oxygen is present, that's a drawback because the oxidation starts to be relevant, so that cannot be neglected at temperature which are around 400 Celsius, that is very low values. And with the reaction that I mentioned to you here, it is written. And so the most important thing is to understand what is controlling the rate of oxidation, and what is it has been underlined here is that the rate of oxidation is essentially controlled by the transportation of the gaseous species which are formed due to the oxidation away from the reaction front, in order, let me say, to discover pure or free materials which is able to react again. And so we do have lines with which we can, in presence of oxygen, make the oxidation low in terms of reaction rate, which can be focused on the, let me say, reduction of this transport process, or again in the protection of the surface with a material which is an oxidation resistant. And usually there are two modes of protect the materials according to what we have said. We can use inhibitors, that is oxygen getters and glass formers, that is materials which are consuming the oxygen, or we can apply, as we said before, a barrier coating with an outside protective layer. This is made, for example, in the second case, by using, in some cases, noble metals, which is going to increase also, like iridium, the cost of our component, or silicon carbide coatings, since silicon carbide has a better oxidation resistance, as we told before, or some non-oxide ceramic materials in terms of coatings, depending, obviously, again, on the type of application we do have in mind. One example to conclude the discussion of today of the use of carbon-carbon composites, even though this object is not more flying, okay, but it is something which has been made, is on the space shuttle, as I told to you. Due to the blunt configuration of the geometry of this vehicle, even though it is a re-entry vehicle from the atmosphere, let me say, we expect high temperature, stressing the materials, but not very high temperature. And just to give to you an idea, if you want, let me say, to have a sort of map of the expected design temperature to which materials used must withstand, they are reported in this slide. And we can see, let me use my pen here, in the nose, we do have the highest values of temperature, as well as, what is it, here on the leading edge. These are the most stressed parts of the vehicle for what it concerns the temperature. And so values, let me say, are not exceeding 1,500 Celsius, even though this is a re-entry vehicles. A different situation is for the sharp vehicles we mentioned, where we can expect on the nose, for example, of the vehicle having a sharp configuration like this one, okay, values approaching 2,000 Celsius. But in the case of the space shuttle, this is the panorama of the temperature during the most stressed phase of the flight. And these are the solutions that have been implemented. And so you see that we do have the solution carbon-carbon here, okay, for what it concerns, what we have just said, that is nose cap and wing leading edge, where we cannot think to use the other solutions which were sorry, used in other parts of the vehicle, and based, for example, on silica tiles or with borosilicate glass coatings, which were used, for example, this one for the high temperature reusable insulation, that is the part which is covering by our tiles, for example, this part of the vehicles. Okay, so we do have examples of something which has a real technical experience, apart from the drawback that he had, and this one, you see, and the leading edge, this one, made by carbon-carbon. Other examples are these, as we mentioned, for example, in ceramic liquid rocket engine components, also developed not by standard, let me say, organization. And other application also we mentioned of carbon-carbon are in the Formula One for what it concerns, for example, brakes, clutches, exhaust parts, due to the high temperature of the exhaust gases, head shields, and this is an example of a brake disc of a Formula One, which is made by carbon-carbon, relying on the positive effect that we discussed last time for what it concerns the variation of the, you remember, the friction coefficient with the temperature. Because if we do have carbon-carbon, you need to make cool your disk. And this is what is done by the pilot in the first row of the Grand Prix. It just to have a constant value of the friction coefficient, and that is a constant efficiency of our braking system, which is quite different from what is going to happen for conventional brake disc, which had, if you remember, a behavior like this. That is what we have in our standard automobiles, for which if we are braking for a long period of time, we need to release our brake, otherwise the braking efficiency is going to decrease in a very dangerous, also sensible way. With this, I think we can close the lesson of today. We have finished our discussion about ceramic and ceramic matrix composites. And since we have entered the area of composite materials, from the next meeting, the next lessons, that is from next Monday, we will start to discuss in a more organized way with respect to those we have very rapidly made during our 4 courses about mechanics of composite materials. As you will see, our mechanical model, they are going to work quite well for composite materials having a sort of elastic behavior, both for the matrix and for the reinforcement. And so they apply essentially, and this is what we have to remember, to polymeric matrix composite reinforced with polymeric fibers or with ceramic fibers, and to ceramic matrix composites reinforced with ceramic fibers. But this will be the topic with which we will start our meeting next Monday. So for today, I finished. If somebody has questions, I'm here. Okay, so no questions. Have a good weekend and see you again on next Monday. Arrivederci a tutti.
Grazie, prof, arrivederci.